Hi there. Today I'm going to help enhance your component recognition skills. So this is very handy for spotting these components in circuit or out of circuit, or say you're at a swap meet or something like that, and somebody's selling a whole bunch of different components in bagfuls. You can take a look in the bag and go, oh, okay, I recognize that. Some of the components I show you are going to be rather common, and some of them are just downright strange. So, we'll start with this device right here. Oh, and by the way, feel free to pause the video at any time if you want to guess what a component is. Say you don't recognize it. So this device here is known as a stud mount SCR, or silicon controlled rectifier. How do I know that? Because it has this protruding gate lead right here. That's not to be confused with just a standard diode. You can see this is a diode here, and there is no protruding gate lead. Now, a lot of the companies, they remove all this stuff. You can see the International Rectifier here was nice enough to leave all the writing on this and even have the direction of the diode written on the body here. A lot of companies that want to protect their designs will take all the writing off. So it's very important to be able to recognize this, and that is a way to differentiate an SCR from a diode, is just look for the gate connection on the upper block here. These are designed to deal with a lot of current. These are very big devices right here. These come in all different shapes and sizes. You can see that there's a smaller one here, and these also come in SCRs. They have little gate leads sticking out of these as well. They're even smaller. Now, they hide Zener diodes inside of these things as well. So not only are just standard diodes in these things, but they put all sorts of different types of diodes in these packages. This little device right here, if you were to see this in circuit, you might think this is an older style transistor, when in fact it is a diode as well. This is found in a lot of test gear. So this came out of a piece of Hewlett-Packard gear right here. So very dependable device. I don't really find that these things ever fail, but good to know if you ever see something like this in a power supply like this. If you can't see underneath the device, this could be very easily confused as a larger style transistor. This is another diode. This is found in a lot of older equipment. A lot of these types of diodes can be replaced with 1N5408s or 1N4007s, just depending on the current rating and the current they have to deal with. They've marked the polarity of the diode on the case there as well. It's very easy to remember with these because the flat disk is the line. Here is another diode here. So this is an older germanium style diode. This is often found in a lot of older radio gear, and sometimes they're even found in probes and things like that. Very easy to identify. Again, a lot of the times there is no writing on these glass cases. When you see a big glass diode like this with a nice big red band on it, it's most likely an old germanium diode, and many diodes will work in place of this. In fact, I use some newer Schottkys that work very, very well in place of these diodes, and I'll talk about that in another video. We'll keep this to component recognition. So, nice device, brand new. This is another odd-looking diode. If you see something like this in circuit, it almost looks like a button cell with some leads on it. This, again, is another diode. No markings really on this. And if we take a look at these right here, these look like some TO92 package transistors with no center lead. See that? They only have 2 leads on them. Very commonly, these things are a thing called a varactor diode or a tuning diode. So this is like a variable capacitor that's controlled by voltage. I'll get into the fundamentals of varactor diodes here in just a little bit, and what we're going to do in the future is design some oscillating circuits around varactor diodes. So it's basically, like those big potato slicer capacitors that you see, like even in the Vitalizer, in the wave meter circuit, that big capacitor. These things here are just like those, but they're in a very small case. Of course, you can't deal with the voltages that those big capacitors deal with, but these usually have a very large range of capacitance. So just by applying voltage to this and having another blocking capacitor in series with one of these things, you can use these things as tuning diodes. That's virtually what they are. It's just tuning diodes, and they come this kind of style here, and I have another one over here. These are graded, and this one here has gold leads on it. This is a Motorola part that's been specially manufactured for a certain device and been tested. Not often do you find gold leads on components anymore. So varactor diodes. In a pinch, if you want to design a circuit and you don't have a varactor diode, you know what works really well as a varactor? A red LED. You know, the old red diffused LEDs? They work great for varactors. Kind of interesting little thing there. Let's see. This is another interesting device right here. I'll hide what it is first of all so you can guess what this thing is. What is this? This is known as a photomodulator, and you'll find these things in a lot of guitar amplifiers. See, photomod there. So one side is an incandescent bulb, and the other side is a cell. So sometimes, depending on the circuit, sometimes we'll even have a neon bulb in this side. This is an incandescent bulb in this side here. So by varying the intensity of the lamp, we'll change the resistance of the photocell on this side. You can get all sorts of interesting effects with these things. These are photomodulators. Again, very commonly found in guitar amplifiers in all sorts of different shapes and designs and sizes and things like that. Whenever you see a little block like this with only 4 leads on it, you can see the 2 squiggly lines. The 2 little squiggly lines right there. And a plus and a negative. This is a bridge rectifier. So it looks like a standard, basically an 8-pin dip, but it's missing 2 leads on it. So if you see something like this in circuit, like so, and they've taken all of this stuff off of the top here, so there's no squiggly lines or there's no plus and minus, and it only has 4 legs on it. Very common that it's a bridge rectifier. So how you'd really determine that is this side would go out to a transformer. And it's very common to have both the AC inputs on one side and the positive and negative on the other. So there you go. That's the easiest way to recognize these things in circuit. When you see a device like this with 3 leads on it, very commonly ICs with 3 leads on them are opto-isolators. Now there's all sorts of different types of opto-isolators. Some have triac outputs, some have SCR outputs, some have Darlington outputs, some have transistor outputs. They have all sorts of different outputs. Very commonly when you see an IC with 3 leads on each side, so 6 leads in total, you'll know that this here is most likely going to be some form of an opto-isolator. Another giveaway for these is the white colored block. You see them white like this. Again, another opto-isolator. Whenever I design anything with an AC circuit and I'm using an opto-isolator to trigger, say, a triac or something like that, I'll use a zero-crossing opto-isolator. If you use just a standard opto-isolator in a circuit that isn't zero-cross, you'll find that the circuit is very noisy. So zero-crossing opto-isolators will trigger the triac at just a little bit above zero-cross or below zero-cross. And that keeps the circuit nice and quiet. Very important. Whenever I design any of the AC circuits, you spend the extra money and you buy a zero-cross opto. It's very, very important. Let's see, what else have I got here? Lots and lots of components. I don't think I'll keep it in order because they're just randomly placed all over the sheet. When you find something like this in a circuit, this is a very old transistor. Yes, they came in all sorts of different shapes and sizes. So if you see something like this bolted down to a chassis, commonly found again in older test gear, this is a transistor. You can see emitter and base right there. Very easily, you can test these things with a curve tracer. Whenever you find a case like this in a radio, and it has 4 leads on it, very commonly these are dual gate FETs. If it has 3SK on it, you'll know that it's a dual gate FET. If this is close to the front end of any radio circuit, you'll also find if it has no writing on it or anything like that, and they have this larger style can on the top, like the normal style can for most transistors is a little bit smaller, like this one, right? This one here is most likely going to be a dual gate FET. Very, very common in lots of older radio gear, and they have 4 leads on the bottom. It's the same thing with this one here. I know this one is a dual gate FET because you can see right from the factory, gold leads, very high quality component, and they have this little spring clip that they've put around all the leads. You have to take this little spring clip off before you use the device. They're shorting all the leads together so that you don't zap the gates. So, it's a graded high quality component, and this is what they do when they basically have these things as a replacement for, say, a piece of Hewlett-Packard gear or tech gear or something like that. They come in a nice package, and they're, they have a grading on them, so they've spent the time to make sure that the device is correct for a plug-in or something like that. All right, I grabbed another batch of components. So, what are these things? Well, these are standard in very high frequency and ultra high frequency work. So these are VHF, UHF transistors. You'll find these things in oscillator circuits. You'll find these things in VHF, UHF handheld radios, little transceivers. You'll even find these things in the front end of oscilloscopes. Now, lots of different types of transistors hide in this package style. You'll find dual gate N-channel FETs, just standard N-channel FETs, NPN transistors, all sorts of things. So I used a dual gate N-channel FET like this in a pan adapter. So on the market, you'll find a lot of 10.7 megahertz IF pan adapters, and a pan adapter allows you to look around the radio spectrum while you're listening to a single frequency in the middle. So wherever you're listening is always in the center of the oscilloscope screen. And so say you're listening to this center frequency here and you see a little pick pop up on the oscilloscope screen over here. If you roll it, you roll that pick into the center, now you're listening to it. So everything that's in the center of this screen, you're listening to. So it allows you to look around the radio spectrum as you're listening to just a center frequency. And these were used in the military a lot to find people hiding around in the radio spectrum. So say there's a really quick signal pop up over here, they could really quickly roll their receiver dial and bring that right into the center and listen to it. And they're known as band scopes, or they're known as panoramic adapters. And I have a bunch of those things. I did a video on a panoramic adapter a little while back. Well, I have made an adapter to take 10.7 megahertz IF pan adapters and bring them down to 455 kilohertz. So you can use these really cheap surplus pan adapters with your standard old communications receivers. It's a little circuit board with an N-channel FET and an oscillator and a bunch of stuff on it. And I'll share that circuit with you guys in the future. So for those of you that are really interested in pan scopes and restoring old receivers and watching around the spectrum, you'll really enjoy that circuit. So I'll share that with you guys in the future. I have so many circuits to share, books and books of them full. So that's just one of the neat little projects. I'll share the circuit board layout and everything with you guys when the time comes. Lots of neat stuff coming. People look at these things and they go, oh no, STK package devices. And yeah, I don't blame you, because the old stereo systems used to use these, except they would only have an STK number on them and they wouldn't say voltage regulator, but they would have an STK number on them. And if you had a stereo system and one of the speakers wasn't working, chances are these guys were the fault. And they were really expensive way back when. Replacing some of these STK package devices was between $40 and $80 to get just a kind of a standard everyday amplifier working. They use these in vertical deflection amplifiers in a lot of the big screen televisions, all that kind of stuff. So you found STK devices everywhere. Of course, they wouldn't say voltage regulator. They would just have a number. They might say amplifier on it, or sometimes they just don't say anything. They just had this number. So whenever people say STK, they go, oh no, STK devices. Well, guess what? A lot of the times you can open these things up and the only fault is a burnt bonding wire, or some of the soldering has come undone inside the package. Many times these things can be fixed, and you just put the little cover back on. Of course, you're opening this thing up and you'll see a whole bunch of components and a jelly in here with bonding wires. If you look at it under a microscope, you can fix these things and they work again. Lots of the time. Sometimes they're burnt right up. You have that scenario as well. But I would say more often than not, I've made these old STK packages work again. They're pretty tough. So don't fear things that say STK. Nowadays, I guess maybe you should, because the kind of stuff has gone missing. I don't think they even make this anymore. But resurrecting these things is a possibility. I'll go through some of these things in the future. Maybe we'll resurrect an amplifier with an SDK, faulty SDK package chip in it. What's this thing? Well, it's a reed relay with a lot of coil. So this would be very easily driven with a vacuum tube circuit, and there's a little reed relay in there. So what this is a magnetic relay. There's two little contacts in a glass tube in the center, and when you apply current to the coil here, the two little contacts close. It's sealed in a glass tube. So they're pretty consistent. So they're a really nice device to use for low-level signals. You'll find that if you use a standard relay on very low-level audio signals, a lot of the time, relays, when they're not energized, they're like this, and then say the coil's down here, you energize them and it does this. Well, contacts inside of relays oxidize, and you'll get crackly, staticky contacts unless they spark. Relays self-clean themselves when you have a little bit of current passage in them. When there's no current passage, the contacts oxidize and they get crackly. The nice thing about reed relays is the contacts are sealed inside of a tube, so they don't do that. Some of the very expensive reed relays even have getter compound inside them. This device right here is another one of those relays. This one here is gettered. Inside here, there's like as you see in a vacuum tube, right? As you see in a vacuum tube, this getter spot here, they have a getter spot in there to keep this, to keep impurities out of the reed relay. You'll find reed relays that have getter spots in them, and some of them even have a bimetal strip that make them kind of pop in and out. Right? So they're very consistent. You'll find those type of reed relays in the turret assemblies for some of the large CNC machines. Some of them that are still in use still use those because they're very consistent. They pop in and out, and they are gettered as well. So they're very, very accurate relays. Again, two contacts sealed in a glass tube like a vacuum tube and gettered. This is one here, and there's another one right here. Right, so there's all sorts of different types. You can see the little tube would be in here, a nice big glass tube inside this thing. So yeah, maybe what I'll do is I'll cut one of these ends off and pull it out here in the future and show you how these things look inside. So nice devices. Lots of coil on these things, so they're very easily driven by vacuum tubes. If you want to make a circuit that controls a relay in some sort of an amplifier or something like that, these older style relays do that. This is another type of relay, but this is called a mercury wetted relay. So they have mercury inside these things, something like a standard thermometer you would get for your house, a little bit of mercury in here, and these are very consistent as well. So these are used in low signal, applications. What I'll do is, I don't know if you can hear this. I'll shake it around, see if you can hear it. Hear that? You can hear it rattling around in there, a little bit of mercury rattling around in there. So these are very commonly used, again, in very, very low signal applications. Nice shiny case on this one, brand new device. So nice little relay right there. What is this? Well, it's an oscillator. These things are found a lot in computers. These are very easily recognizable by the case and the little tab on the corner there. You see on the top here, if I can stop the light from glaring on this. I don't know if I can, it's so shiny, I don't even think I can read anything on the top there. So yeah, it's just too shiny. Too shiny and too much light. But anyways, oh, there it is. Let me turn that around. Give it a tilt like that, there you can see. That's the frequency on top, 14.31818. And this is just an entirely fixed oscillator, so you can put a supply to this thing and you'll have that frequency come out of it. These are very handy to use in all sorts of applications where you need a fixed frequency and something where you don't want to trim anything. You just put this thing into the circuit and away the thing goes. They're made by all sorts of different types of companies. What is this thing? This is a solid state vacuum tube known as a tubester or a Fetron. So that they were, under all sorts of different names, and you'd often find these things in a lot of high-end test gear. So what would happen is, like, this tube would say replace a 6AK5 or some other type of, vacuum tube. I'm not sure the exact replacement of this one, But these would fit in there and you'd get really consistent results, and it would lower warm-up time and things like that. Now, there's a bit of a trick to this stuff. A lot of the times when you put these little Fetrons into a device, the device itself was calibrated to work at a certain temperature. And that was the temperature that the vacuum tubes would bring the device up to. So when you put a Fetron inside of, say, a calibrated piece of equipment, a lot of the times it would throw the cal way off and they would never really quite warm up. So they would be in that area of movement. So whenever you're designing anything around a vacuum tube, of course, temperature compensation is a really, really big thing, especially in oscillator circuits. Oscillators are very finicky with temperature because when you have a capacitor and things expand, if they expand, the components grow apart. That changes the capacitance. The capacitance will go higher into the picofarads, if you want to look at that as lower capacitance, or it goes higher into the picofarads. So say it was 10 picofarad and it expanded, it might go down to say 5 picofarad, something like that. The expansion will cause that movement. So if it goes, say, from 10 to 5 picofarad, what's going to happen with that oscillator circuit? The frequency is going to go high. All right. So anytime you take a capacitor and remove some capacitance, all right. So say it's 100 picofarad in an oscillator circuit. If it drops to 80 picofarad, the frequency is going to go up. If the capacitor went from 100 picofarad to 200 picofarad, the frequency would go down. So something to keep in mind. At any rate, these are very handy in circuits. These were used in voltmeters and, again, a lot of Hewlett-Packard gear would have these, and these were even plugins for some Tektronix modules. Known as a Fetron or a tubester. If you find these things, there is cross-references for these. I have an entire box full of these things. One day we'll cut one of these things open and take a look inside. Maybe we'll put a tube in a circuit and a Fetron in a circuit and compare them both and see how they compare to each other, to its equivalent vacuum tube. That'd be kind of fun, wouldn't it? Another reed relay, except this one here has got 4 of them inside it. Actually, no, there's 5 in this one. There's 5 in this one. 1, 2, 3, 4, 5 reed relay tubes inside this one, and the coils. So the coils are right at the end here. So this is designed to move a lot of signals. So you'll find these in lots of interesting types of circuit. A lot of this stuff came out of older telecom circuits, things like that. You'll still find these things. You find a lot of reed relays and things like that, and attenuators and things where you need a very accurate contact. Let's see. What is this thing? This thing is a temperature sensor. You find these things, there's a little bimetal button in here. When you heat these things up, they kind of make a pop noise and they'll turn on or off depending on how they're configured inside. These things are found in all sorts of different pieces of electronics. They put these on heat sinks and large amplifiers, so if they get too hot, the thing shuts the amp off. You find these things in coffee makers, microwaves. You find these things all over the place. So if you see something like this screwed down, usually they're like this, right? They'll sit like this because the tabs are here and you need to get to the screw tabs. So they're adjustable, right? You can move these wherever. So you'll find these things tightened down like so. And they're usually to either a heat sink or something that's going to, be getting very, very hot. So this monitors this. You'll notice in coffee makers, they will have these things right on the element itself. And then in series with this thing, they'll have a thermal fuse. Because these things only have a certain cycle life. So that little bimetal strip will, pop on and off. They kind of make a like a very tinny little noise when they pop in. So they're on and off, on and off, on and off to regulate the temperature of the element inside of a coffee maker. Well, what ends up happening is that little bimetal strip sometimes gets weak and it jams up and the thing sticks on. So what happens? Well, your coffee maker goes into thermal overload and the element just stays on. Well, it goes on hotter and hotter and hotter and hotter. And then the fuse that's in line with this, that's also usually strapped right to the element of the coffee maker will end up just opening. So that's the safety device that's in line with these things. So usually when you find that your coffee maker is burnt out, it's usually this device that's stuck and then the thermal fuse goes away. Of course, sometimes the elements short and things like that as well. That's a real common failure point in coffee makers, in anything where these little devices are cycling a lot. Again, they only have a certain cycle life, right? The little bimetal strip wears out. Let's see, what else have I got here? These are commonly seen. These are wire wound resistors, not to be used usually in any type of an RF circuit because there's a wire wound in there, so it actually forms an inductor. Great for DC circuits and things like that. But any type of high frequency work, you want to keep wire wound resistors out of. So it's a 5.1 ohm 5 watt resistor, and these are used in all sorts of different applications where you need to have a resistor that's going to be dealing with a little bit of current, right? And these come in all different shapes and sizes. I've got big ones and like that one like this. This is the 50 watt version. Again, wire wound inside this thing, so not good for any type of an RF circuit. You want to keep any type of a wire wound circuit. Say you were making a dummy load for an HF transceiver, VHF transceiver, whatever. You can't use any, say the resistor said 50 ohms. You can't use it. It's a wire wound resistor. It just doesn't work because it's an inductor, right? It's very inductive. So whenever you're making a dummy load or anything for RF service, that's the reason you see these types of resistors here. I'll grab this. You see these types of resistors. This is a carbon composition resistor, and they're not very inductive, unlike a non-inductive style resistor, right? Anything with lead length is an inductor at a certain frequency, all right? But when you're dealing with HF frequencies and dummy loads, usually this is this would be well above it. This thing would be inductive way up high in frequency, right? So no wire wound resistors in any type of RF circuitry. If it's in the supply line for it and there's a filter on the other side, that's absolutely fine. But the thing is if this is in line anywhere in the signal path, absolute no-no. No wire wound resistors in oscillators or any type of RF circuitry. Always remember that because that'll make or break any type of a restoration. You'll see a lot of these types of resistors in applications, RF application. Even to this day, you'll find carbon composition resistors of some value just because they're, either a very, very low inductive type of resistor. So non-inductive, I should say, type of resistor. So of course they have plugs in the end, right? There's a little wire plug that goes into each end, and then there's the little carbon resistor element in the center, right? And of course lead length again is inductive at different types of frequencies, right? So like cell phone antennas, right? Very, very small. That's an actual antenna right there, right? So just depending on what type of frequency you're working with, anything can really become an inductor. So, but for most application, you'll find these things in like HF receivers and stuff like that because this is invisible in that circuit, right? That is not really acting as any type of an inductor there at all. You'll find this invisible in HF receivers and even some types of VHF receivers, short lead length and things like that, right? You find these common in older CRT type monitors and things like that in certain circuitry around the flyback. So. This is an Allen Bradley style of resistor, and what you often hear me slagging roundies, and this is a roundy style. This is a really big roundy, okay? These things are very prone to drift if they've been left in a moist environment or, somewhere where the environment hasn't been controlled. It seems that moisture gets into these things and it causes them to move around in value quite a bit. So whenever you find a roundy like this, it's always good to test it. If you test an entire radio and all the roundies are good, it's probably good to leave them in there. All right? You don't want to leave them in if you find a bunch of them that have really moved. That means that it's usually been in a bad environment or they're just really bad resistors. You'll find that the Allen Bradley style with the squared off ends, you can see how these are squared off and these are rounded, right? So the squared off ends are usually a much better resistor, and they have a coating on the case. You can see how it's kind of shiny, which stops moisture ingression into the device. So something to keep in mind. And these are not to be confused with these. You see the body's green. Whenever you see a green body, it's usually an inductor, not a resistor. Now they color code them the same or very close to resistors, but green bodies usually indicate inductors. Always keep that in mind. So if you see color codes on something that's green, there's a coil in there of some sort. And they come in all sorts of different shapes and sizes. Here's another one here, right? And I'll talk about how to read these things in the future as well. That is not a resistor. That is an inductor, 100 microhenry inductor right there. And here's another inductor right here. This is another one. You can really tell these just by looking at the shape of the device. They're very rounded. All right, there's another little inductor right there. And then if you're working on older equipment, you'll get inductors that look like this. Basically, it's a ceramic tube in the center. And these things are inductors and sometimes capacitors. So this device right here is an actual capacitor. This one here is a capacitor that's on a piece of tubing inside, but you'll also find inductors wound like this on this same type of form. So these can be a little bit tricky. So again, the best thing to do with something like this is measure it, see what you've got, and then compare what you've measured to what's on top and see if it compares to either an inductor. If it is a capacitor, you'll notice that it'll be an open connection. Very easy to find out. If it's an inductor of some sort, you will find that there will be resistance between these leads. All right, not to be confused with a shorted device or something like that. So lots of things hide in this particular type of package. And of course the color coding would be different and things like that, right? Again, this one here is a ceramic capacitor, but inductors will hide in this as well. Whenever you see something like this is an extremely high quality product. These were all graded. Now, Lenkert was much like Tektronix. They made their own in-house parts and graded their own in-house parts, and they had very stringent qualifications or very stringent specs for all of their stuff. So if you ever find a bunch of old Lenkert capacitors like this, scoop them up. They're great devices. These things don't leak. They've been around forever, and they just do not leak. Really, really high quality stuff that hides with inside pretty much anything that says Lenkert. They were right up there with Tektronix. Let's see. Here's another one that looks like this resistor. You can see that, except this one's green. This here is another inductor. Again, it's kind of a green speckly kind of body on this. Some of the green's probably gone on this, but again, not to be confused with a resistor. They look like roundies, but with a green body, that means that there's a coil hiding inside that thing, so it's an inductor. A roundy style inductor. These things are fine. They usually, there's nothing goes wrong with these things ever, except they open, all right? This is known as a parasitic trap. So you'll find things like this hiding inside of HF transceivers in the final RF section. So what happens is, in order to stop the final section from parasitic oscillation, they put a carbon resistor inside a bunch of, just usually a few turns of wire. And this is known as a parasitic trap. I'll get into explaining how parasitic traps work and how the RF travels and everything through these things in the future. If you're ever testing a device like this, what you want to do, even though that the resistor looks fine in the center, you want to open up one end of the resistor and measure it, because in RF service, these things fail open, but they look like they're not damaged at all. They look absolutely pristine inside that coil, but the resistor will be open, and that will greatly affect the tuning and loading of your HF transceiver. Again, I will touch on this when we restore an HF transceiver together. So I have a whole bunch of HF transceivers. I've got some big old AM transmitters we're going to restore. We're going to even do some really nice audio modifications to those things as well. I've designed a bunch of audio circuitry for some very nice AM use. I've designed lots of this stuff for HF radios in the past. Kind of well known for that. At any rate, this is another style of capacitor. So this is a disc ceramic style capacitor. These are great for RF bypass. Never, ever use these type of ceramic capacitors, Z5U rated, in any type of an oscillator circuit or anything like that, or the thing will drift around the band like crazy. So these things move around in capacitance like crazy when you heat them or cool them. All right. This is completely different than this little capacitor right here. So this is another ceramic type of capacitor, but there's something very interesting about this. This is a very special build. This is known as an NP0 style capacitor. How do I know that it's an NP0 style capacitor? Because on the top, they put a little black hat on the top. So they've dipped it into some a black liquid. And that's how you tell an NP0 style capacitor from just a regular style disc. Whenever you see a capacitor like this with a little teeny black hat on the top of it like that, NP0, very good capacitor. These can be used in oscillator circuits with no problems. An absolute world of difference in a ceramic capacitor compared to this. Again, good for RF bypass, in taking RF to ground on, screen grid pins and things like that, and all sorts of things. Shouldn't be used in any type of an audio circuit. Stay away from ceramics in any type of audio circuit, again, because of their inherent microphonic qualities. I showed that on another YouTube video, so keep that in mind. If you're ever designing an amplifier, do not use any type of ceramic capacitor in the audio signal chain. This is a polystyrene capacitor. You'll find these things in a lot of oscillator circuits and high frequency circuits. They are very temperature stable, but you have to be careful with external temperature because they are soft. The polystyrene will melt very easily, so you don't want to mount these things close to any type of a vacuum tube. You want to keep these usually under the chassis, away from any style of heat. If you do connect this to a vacuum tube pin that gets hot, leave lots of lead length if possible to act as thermal decoupling so that you do not heat the polystyrene. If you heat the polystyrene, you will cause a capacitance change. So you don't want to do that. Very, very good capacitors. Polystyrene capacitors are top notch. But if you're building an oscillator circuit, you would want to go for a mica capacitor over a polystyrene if possible. Mica capacitors are extremely stable under, wide temperature variation, even externally heated, and they come in all sorts of different, styles and sizes. This is a domino mica capacitor. Now, when you're working on some older radios, they hid paper capacitors inside these packages. Now, it's not common. These are much more commonly mica capacitors, but they did do that way back in the day. They did put paper inside these, so you need to know. If this is in an oscillator circuit in any type of a radio, so in the, how you tune the frequency on a radio, the oscillator circuit inside that radio will have a capacitor like this inside it. It's very advisable not to change these capacitors. These very rarely fail. They do fail, but they rarely do fail. And if they haven't failed, a lot of these components have been hand graded at the factory. So they have a person on a line grading these things so that the radio that they're putting this thing in, the dial accuracy will align with what they've got on the dial. So if, say, you have, for example, like this one here is 22 picofarad? Yeah, 22 picofarad. All right, so just say you had a 22 picofarad capacitor and it was a domino style like this. It might actually be graded to 25 picofarad even though it says 22 on it. You don't know that. And then very, very common in older radio circuits. So around the oscillator circuit, if possible, never change these things. They very rarely fail, and if they do fail, you're stuck with it. You do have to change it. But don't create any extra issues by doing that. Okay, I grabbed some more components. So, what is this thing? You can see I've removed it from circuit. This is a plunger style variable capacitor. These are used in oscillator circuits for tuning. So, usually in higher frequency devices, remove the little adjustment screw on the top. You can see the little plunger on the bottom, and that just moves in and out of this little area right here. So if this was in like this, it would say, for example, be, say, 15 picofarad, and maybe that would be 10 picofarad, and then that would be maybe 2 picofarad. So as this is moving out of this, so as you're moving this away from this, you're changing the capacitance. And of course, the finer the thread, the nicer it is. You can see this is on a nice fine thread, so it allows for very minute adjustment. Again, found in oscillator circuits and things like that. You can even tune RF stages and high-frequency receivers and things with devices like this. So if you see something like this and you know that, say, the radio has failed, or say the device that this thing is in has failed, and there's a whole bunch of these things in a line, when you're dealing with high-frequency oscillator circuits and when you're dealing with any type of RF stages that are in very high-frequency or ultra-high-frequency devices, if you detune one of these things on a lower band, a lot of the times they couple. So these things will couple. So you have to start at the lower band, tune the lower band, and work your way up to the highest frequency. So if you detune one down the band, it actually messes around with all of them. So there's an order for the alignment. So unless you know something like this has failed, and it's very uncommon for something like this to fail, it's not advisable to move the plunger around in these things, especially if the alignment is good. If you're into trying to do another alignment on something, that's absolutely fine. You can do whatever you want, move the things around, but just, keep that in mind. If you move one around down the line, usually it affects the higher frequency because there is some form of coupling in these circuits. It's really quite common. Something to keep in mind that a lot of service techs don't know, and that creates havoc, especially if you have to go through and realign. Say you think the thing's faulty and you mess with it, right? This is an RF choke. So you'll find this in a lot of older tube type receivers and transmitters. You even find this in some modern equipment. So these are very nice RF chokes. So if you see something like this, that's what it is, with 3 little bobbins. Sometimes they have 4 or 5 little bobbins on them. And there's usually no rating written or anything on these things, so you got to measure them to find out what they are. RF choke right there. Here is another small inductor. These very rarely fail. You'll find these again in oscillator circuits. You'll find these things in receivers, transmitters. You'll find these things in ham radios, CB radios. They're pretty common, these little things. So this is the color coding on the top. I'll talk about reading the color coding on this stuff in the near future. This one here is 100 microhenries. That's the rating of this one. It's brown, black, and then brown on the side there. Again, I'll talk about this little blue body on the thing. That's how you identify these things. One point in time, I had one of those in a transceiver that was shorted, and it stopped the entire oscillator section on all the bands. Very uncommon. Very, very uncommon. But it still happens. What is this thing? Well, you're probably going, oh, come on, that's a diode. Well, it's not. It's a capacitor, and it's sealed in a glass case, just like a diode. It's a little surface mount capacitor. These are used in rough environments and in moist environments, so things that are exposed to the elements to keep things nice and accurate. So what I'll do is I'll just zoom on into this here. I'll just zoom my camera in, get as close as I can, and there it is. So you can see the little surface mount capacitor inside. See how it's a little brown chip? That's a dead giveaway for a surface mount ceramic capacitor. See, the ratings are nicely written on the side. It says 102, so that's 0.001 microfarad, or if you like, 1,000 picofarad. And if I slowly rotate it, you can see it says 50 volts on the side. It's a 50 volt capacitor. Now, if you look inside the glass, you'll see that there's a little ceramic capacitor in there, and you can also compare it to a standard surface mount capacitor. That's how they look. So whenever you're working in surface mount equipment, if you find a little rectangular block in there like this, and it has a chocolate brown body on it, those are usually always ceramic capacitors. So that's the way you can identify these devices in surface mount equipment. Not to be confused with the resistor, which is right here. So there's a small resistor. That one says 103 on it, so that's 10k ohms right there. So that's what surface mount resistors look like, and that's what a surface mount capacitor looks like. You can see the difference in the color of the body. Some manufacturers are tricky, and they do this. They put them upside down so that you can't see the ratings. So it just depends on who you're dealing with. So I've come across that myself. So these are 1206 size parts. The little part inside there looks like it might be 0603, and it's pinched between 2 small end caps in a little sealed case. You can see it's nicely sealed. So not always are little things that like this diodes. There's capacitors hiding in them as well. Here are some small tantalum capacitors. Now, a lot of people, they say, I really don't like tantalum capacitors. They seem to fail a lot. Well, if you operate these things within parameters, they are usually very, very dependable. And there are quite a few advantages to using tantalum capacitors. It's the reason that you find them used in bypass circuitry around ICs and all sorts of things like that. Nowadays, capacitors are changing a lot in technology. So for bypass application, you can use a small ceramic capacitor like the one that I just showed you. They're going up to 10, 20, 30 microfarad now in very small packages. So these here are still very, very good in timing circuits. So if you want a very accurate capacitor that's not going to move around a whole lot with temperature in a timing circuit, say you've designed a circuit that is going to time out after 40 seconds or something like that, and you want it to remain around that. If you use a tantalum capacitor, it's going to be pretty accurate. If you used an electrolytic capacitor, it'd be all over the map. So electrolytic capacitors, they change with temperature wildly. So this is where these capacitors are still preferred in timing circuits and things like that. Things where you need accuracy, they're still really good. Even ceramic capacitors, the newer ceramic capacitors that are, say, 10, 15, 20 microfarad, something like that, you wouldn't want to use a lot of those capacitors in timing circuits. So there's quite a bit of design thought around making things that deal with time and frequency, and I'm going to go over that in the future here as well. Again, we'll talk about making timers and variable frequency oscillators and things like that, and how to stabilize them, and how to design something and make your design solid so that it's not going to be drifting all over the map. That's the biggest enemy in any type of an oscillator, in a timer circuit, or anything like that, is drift, either thermal drift or voltage, caused by voltage, things like that. You got to get that drift right down to an absolute minimum. The sign of a good oscillator circuit is when you can achieve an oscillator that's equal in stability to something that's crystal controlled. So these are tantalum capacitors, really good devices. You'll find me using tantalum capacitors in lots of things, and you'll find them being very dependable in my designs. So I'll just zoom on out here and get these out of the way. What else have I got here to show you? So this here is a resistor array. So you'll find these things usually around switches and things like that, or anywhere where you need some form of a pull down or pull up resistor. There's a whole bunch of resistors here in a line, and they're configured in different ways. So they look like this, and they look like this as well. So whenever you see an IC that is this kind of a color, it's usually a resistor array. That's how you tell. It's just by that kind of a mustardy type of color. And again, they're configured in all sorts of different ways. You have to look up the part number on top of the resistor array or make measurements to figure out what's going on inside a block like this if they've taken the numbers off. Again, which is common when you're working on these things. So two types of resistor arrays right there. What is this? Another plunger style capacitor. This one is gold plated and designed for high frequency use, very high frequency use. You'll find these things in, again, VFOs and in oscillators and RF sections and things like that. Very accurate device. What's this thing? It says Signalite on it, and it says 82, Z82R7. This is an 82 volt regulator, and it's very, very, very stable. So these are great regulators. As you can see, the tube is gettered inside and everything. So if you find something like this glowing in a circuit, these are commonly used in some of the higher end pieces of test gear. So I find it handy to have these things around just in case I need to replace one. Now, of course, if you're very careful in the way that you put a Zener diode in place of something like this, sometimes you can get away with it. But, I like to put in the original type of component. So this is an 82 volt, equivalent to an 82 volt Zener diode. They glow orange just like a neon bulb, and could very easily be confused for a neon bulb that might be a little bit burnt out. But its purpose is to regulate. And let's see. You see a device like this, and usually older electronics, 3 legs on it as well, germanium transistor. something that might be a little bit more common for some of you out there. Extremely desirable by people who make guitar fuzz pedals, things like that. Extremely desirable with those people. Everything has its value to somebody. What are these? These are 2 relays, another 2 reed-style relays, except they're sealed inside of the block. Again, this looks like a larger IC with only 4 pins on each side and a bunch of pins missing in the center. So whenever you see these inside of a device, a little block like this, it says Hamlin or Magnacraft on it, you'll know that this is a relay. Now, these are configured in all sorts of different, configurations. Some of them are, single pole, double throw. Some of them are dual, single pole, single throw, normally open. Some are normally closed. It just depends on the relay manufacturer and what they've done. So a lot of the time you have to either look up the number, locate the coil leads. If you haven't, if they say the number is missing again, locate the coil leads. It's very easy to do by ohming it out with a meter, and then just experiment. Once you locate the coil leads, you can energize the relay and find out where the contacts are around it. And if there's enough interest in, searching out and finding out how these things work in the future, I will do a video on, basically finding out how these things, how they're wired inside externally, basically looking inside the device from outside without having to crack it open with an ohm meter or with a curve tracer as well. This is what is known as a compactron vacuum tube. And the reason that they called them compactrons is because they're trying to make things more compact. So they're taking more vacuum tubes and fitting them within one glass case. So this is 3 triodes in one glass case, whereas say a 12AU7 or a 12AX7 would only be 2 triodes. Again, trying to make things more compact. Now, these tubes are great to make audio amplifiers with. There's 3 amplifying stages in here. So if you need 2 amplifying stages and say a phase inverter, it's basically all in one vacuum tube. These things are great to build small circuits with. Down the road, we are going to make a very neat radio receiver out of one vacuum tube. We're going to use a compactron vacuum tube and design an entire radio receiver around one tube. That should be a lot of fun. And it will perform very well. So that's coming up here in the near future. So there's a lot of different styles of compactron tubes. Some of them are bigger, some of them are wider. They are used in vertical service, horizontal output service, just as amplifiers. Some compactron tubes are extremely expensive just because of where they've been used in the past. Some compactron tubes have a real big name because of the amplifier that they were used in the past. So you'll find that with some of them. This is a pretty generic compactron. This is a 6U10, and they make great audio amplifier tubes. In fact, they make a great tube for doing lots of different projects with. So compactrons have 12 pins on the bottom, and the little exhaust tip is right there, so they draw the vacuum there, and then they usually flash a getter on the side. Sometimes the getter's on the top, but it's nice when the getter's on the side. If you're going to use this where it's going to be seen, you get the little light of each triode lighting up inside this one device. So lots of really neat stuff coming. Nice thing about glass vacuum tubes in general is if you don't have a data book or the numbering has been completely wiped off and you don't know what it is, you can very carefully follow the pin to where it goes inside the vacuum tube, and you can draw exactly what's inside this vacuum tube on a piece of paper. You can draw the schematic of what's inside, and I've done that many times. If you're interested in seeing that process, you can let me know down below in the comments, and I'll show you guys how to do that. Of course, this works only with glass-type vacuum tubes. I've got tons more components I could show you, but this video is already getting quite long. If you're interested in knowing more about a lot of different components, more surface mount stuff, more through-hole components, more stuff that you would find in point-to-point wiring, you can also let me know down below in the comments. I hope you enjoyed this video. If you did, you can let me know by tapping the heart symbol below, and there'll be many more videos coming like this very soon. Again, tons and tons of components. What I've shown you today is, just nothing. It's just a little drop compared to what I could show you. There's so many different styles of components and, designs of components and lots of things hiding in different cases. So lots of really neat stuff coming. All right, I'll see you very soon. Bye for now.